Today we're going to continue talking about polynomial functions and their graphs. So here we go. You're going to be asked to graph these polynomial functions today based on its zeros and whether they cross once or just touch and turn, and their symmetry, how it should look, and a little bit of algebra. Okay, so first of all, we can use symmetry to help us graph these. If we know our function has even symmetry, algebraically what happens is when you change your negative x's to x's, none of the terms change signs after you simplify. Okay, that's algebraically. Graphically, if you type the function into y1 and you look at it, if the y-axis cuts your graph exactly in half, in other words, the right side is a mirror image of the left side. In other words, if I took this and I drew it on the other side, I would get the same picture. I'd have to flip it. You're not coming over here like this, you're flipping it over. That is even symmetry. I can do it with, I can just take this image and flip it horizontally, and you can see how there's my x-axis and y-axis, and I flipped it over, so now x is over here, y is still up there because it just flipped over, and it's the exact same picture. That's even symmetry. For odd or origin symmetry, okay, algebraically you change all the x's to negative x's, and if all of the terms change signs, then we say the function has origin or odd symmetry. And what you can do is, if you type it in a graphing calculator, graphically what it looks like is, if you could picture taking this half, okay, and reflecting it twice. If you can reflect it twice and it ends up mimicking this side, then it's odd symmetry. So if I turned this upside down, it would do this. If I just turned the red side upside down. In yellow, it would be like that. Now if I took the yellow and I reflected it over the y-axis, notice I get the other half of the graph. So after two reflections, the red side looks like the green side, which means it has odd or origin symmetry. You can also look at it, again with a computer, you can click that object and reflect it. And if I reflect it over y, just like I did up here, I don't get the same picture back, which means it's not even. But if I reflect it again, notice, here's my x, here's my y, and I flipped it, here's my x, and here's my y. I flipped over the y-axis. Now if I flip it again, reflect it again, I should say, notice that my x is here, but my y is upside down. Wherever it went, I cut it off, I guess. Alright, but notice now it looks just like the beginning. So after two reflections, it looks like the beginning picture, which means I have odd or origin symmetry. If there's no symmetry algebraically, when you change all of your x's to negative x's, and what will happen is some of the terms will change signs and some won't. That's a clue that there's no symmetry. Graphically, if you type it in and you look, obviously it doesn't reflect over the y-axis, and I can even do it on the computer. No, it doesn't look the same. And if I try and reflect it again, it still doesn't look the same as the original. That means there's no symmetry to the graph. Alright, to graph a polynomial function, okay, they've got quite a few steps here. But if you follow them, it really does make it easy. Okay, first you're going to use the leading coefficient to determine the graph's end behavior. In other words, you're going to figure out what your tails are going to do. Are they both going to point up? Are they both going to point down and wiggle in the middle? Is one going to point up and the other one down, or is one going to point down and the other one up? Okay, so you're going to decide, because you need to know what the ends are going to look like, so you know what's going to happen in the middle and how to connect them. Okay, so that's the first thing you're going to decide. Then you're going to find your x-intercepts. You're going to set f of x equal to 0 and solve it, either preferably by factoring. Okay, actually you want to factor. If there is an x-intercept at r as a result of this, in the complete factorization of the function, then if k is even, you know that the graph is just going to touch it and turn around there. If that degree is odd, the graph crosses, it's going to cross through the x-axis at r. And finally, you'll know that the degree has to be bigger than 1 if the graph flattens out. And I'll show you what that looks like when we get to a problem. Okay, so you're going to decide that. You're going to mark your zeros basically and decide if it's going to touch and turn across. Then you're going to find the y-intercept by making x 0 and plot that point. And then you're going to use symmetry, if it's helpful, to connect those dots and draw the graph. And then you can also use the fact that the maximum number of turning points of the graph is n minus 1. What that means is, let's say that I have a third degree function. What that means is there's only going to be 2 turning points. What are you talking about, miss? Well, if I have a third degree, we know our tail is going to point different directions. Okay, this is positive, so my second tail has to point up. My first tail has to point down. But when I connect them, I can only have 2 turning points. So there's 1 turning point. So it's going to come back down, then it's got to turn 1 more time to connect to the other tail. This is a degree 3 with only 2 turning points. Okay? So we can use that fact. Alright, so here we go. They want us to graph this. Well, the first thing is to determine the end behavior. My degree is 4, which is even, which means I'm going to have my tails pointing the same direction. We have same tails. My leading coefficient is positive 1, and positive means that both tails are going to point up. Okay, so I know that both tails are going to point up, and since it's 4th degree, it's going to have 3 turning points. So to connect here, I've got to change directions 3 times. So once, twice, 3 times, and then I can connect. So I'm expecting something looking like that. Okay, so there's the first step. Second step is finding the x-intercepts, and it says set the function x to the 4th minus 2x squared plus 1, set it to 0, and factor it. Now, you're going, how do you factor that? It's not a quadratic function. You're right, it's not a quadratic function, but it is, you can use quadratic techniques because this degree right here is half of that degree right there. As long as the middle degree is half, exactly half of the first degree, then you can still factor. The only difference is, and this should be an easy factor because a is 1, the only difference is normally we put x and x here when a is 1. But now I need x to the 4th when I do this multiplication. X times x is x squared. To make it x to the 4th, I need x squareds there. And really, if that makes sense to you, awesome. If it doesn't, then just remember, whatever the degree is on the middle is the degree of the factors when you're doing quadratic techniques. Now, factors of 1 that make 2 are 1 and 1. C is positive, which means they both get the middle, and I factored it. Okay? So now I'm going to solve it. So I said x squared minus 1 equal to 0. X squared minus 1 equal to 0. Then I'm going to solve these. Add 1, x squared equals 1. Square root, x equals positive 1 and x equals negative 1. Solve the other one. Oops. Solve the other one. Add 1, x squared equals 1. Square root, x equals positive 1 and x equals negative 1. So, altogether, okay, these are multiplicity 1s because, don't think of the square. I mean, it's going to end up being multiplicity 2, but not because of that square. The multiplicity, this is x equals 1, multiplicity 1, but because the second factor yielded the same thing, I actually have x equals positive 1 with a multiplicity of 2, which means it's just going to touch and turn there. And I have x equals negative 1 with multiplicity 2, because see how it happened twice, which means it's going to touch and turn there. So I'm going to plot those points, positive 1, negative 1. I know that both arrows are going to point up, and I know that I have to change directions 3 times. So I'm going to come down, hit it, but just don't pass through. I'm going to touch and turn. So I'm going to come back up, and then I have to change directions. Again, I don't know how high to go up, but I know I have to change directions to come down to here. That shouldn't be pointing. Okay, and then once I touch here, I touch and turn, and I can head back up to my arrows. Okay, and that should be what my graph looks like. Now the only thing that I'm probably not accurate on is how high this goes right there, which if you want, that's why they want us to compute the y-intercept. Okay, so if I compute f of 0 in my original function, I would have 0 to the 4th minus 2 times 0 squared plus 1. That's 0 minus 0 plus 1 is 1. So it's going to pass through the ordered pair 0, 1. So I can plot that point, and then I know to come down, just go that high, turn around, and come back up. Okay, so there's my y-intercept. And then again, I didn't really think about it, but I kind of did. It's going to be even, right? So the y-axis has to cut it in half, and this side has to mirror that side. And I did type it in the graphing calculator, and we're pretty darn close. Okay? Alright, you try this one. Hit pause, come back when you're ready. And I hope you got B. If you did not, let's look at Y. Okay? The first thing is end behavior. My highest degree, this is written wrong and he's trying to trick you. This should be negative x cubed plus 3x squared if you wrote it in proper order. Okay? So my degree is 3, which is odd, which means my tails are going to be opposite tails. My leading coefficient is negative 1. Negative means that the second, or that the right tail has to point down. So I'm expecting this tail to do this tail to do this, and it's only going to change directions twice. Once, twice, and then it's got to connect to its other tail. So I'm expecting something that looks like this. Okay, I need the first tail up and the second tail down. First tail up, second tail down. First tail up, second tail down. This one's out, this one's out, because their first tail is down and second one's up. Okay, so now I need to get my x-intercepts. So I take my function and I set it to 0 and I factor. To factor when there's only two terms, you look for a GCF. I can pull an x squared out. If I pull an x squared and divide by it, I get negative x plus 3 equals 0. So now if I set them to 0, x squared equals 0. This is going to have multiplicity 2. And negative x plus 3 equals 0 is going to have multiplicity 1. So if I solve the first one, square root, x equals plus or minus 0, which 0 doesn't have a sign. 0 isn't positive or negative. So x equals 0, but it's got a multiplicity of 2. So at 0, it's got to touch and turn. Well, unfortunately, they both do, so I still don't know any better. Okay, so we've got that, and then we have, if I solve this one, minus 3, negative x equals negative 3, divide by a negative, and x equals 3, multiplicity 1. So it's got to cross through at 3, and it's got to pass through, and this one doesn't, so now I can tell not. My y-intercept, I already have it because it passes at 0, 0. The only thing you might do is to figure out how high this thing goes. I don't know, you could plug in either 1 or 2. If I found f of 1, I would have 3 times 1 squared minus 1 cubed. This would be 1 times 3 is 3, minus 1 cubed is still 1. 3 minus 1 is 2. So that ordered pair would be 1, 2. And that still didn't really tell me how high to go. I guess I'd have to plug in that one. Okay? But again, it gives you a pretty good idea. Alright, so how do you graph a polynomial function using graphing technology, end behavior, intercept, symmetry, and max number of turning points? Alright, well, can you basically describe those steps in that yellow box? If you describe those steps in the yellow box on a couple slides back, that's how you do it. Okay? Oh, we can answer this one. Given a function of degree n, at most, how many turning points can the graph have? N minus 1. Okay. The zeros of a function are located where on the graph? Yeah, we can answer that one too. They are the x-intercepts. Alright, so now I'm just going to give you some homework help to give you some idea of some quirky things that are going to happen. Part of your homework, there are going to be several parts. They're going to ask you to find the zeros and state the multiplicity of each zero as even or odd. Then you have to write an equation just like we did, okay, expressed as the product of factors of the polynomial function that might have each graph. Use a leading coefficient of 1 or negative 1 to make the degree of f as small as possible. And then it says use both the equation in part B and the graph to find the y-intercept. Okay, so right now I'm looking at my window. This thing goes from -3 to 3 and they're counting by 1. So each tick mark counts as 1. Okay, so this shows me that x equals -2, and I know that it has to have an even multiplicity because it touches and turns. Okay, this tells me that x equals -1, but it's got to have an odd multiplicity. And this one over here, this says that x equals 1. It also passes through, which tells me that it has an odd multiplicity. But do you see how this one goes straight through, but this one kind of flattens out before it passes through? That's what it was talking about, saying whatever your multiplicity is, if it flattens out, if it's, you know, like this, you get what I'm saying? Instead of passing right through like it does at -1, at +1, it kind of flattens itself out a little bit. That tells me that, I mean, normally if you're trying to write a function with the, where am I going? When you're trying to get the degree of f as small as possible, the smallest even number would be 2. So I would say that an even multiplicity would be 2. Obviously, the smallest odd number is 1. This one will work with 1 because it doesn't flatten out, but this one has to be bigger than 1 because it flattens out here. So the next smallest odd number is 3. Okay? So I'm going to say that this one has to have multiplicity 2, this has to have multiplicity 1, and this has to have multiplicity 3. Now, how am I going to get these zeros written as, how am I going to turn them into factors? Well, what you do is you take each one and you put 0 back on the right. So add 2, I get x plus 2 equals 0, which gives me a factor of x plus 2. Okay, then I'm going to do my next one. X equals -1. I want 0 back on this side. So I'm going to add 1, I get x plus 1 equals 0. That's my factor. And then my third one, my x equals 1, minus 1, I get x minus 1 equals 0. There's my factor. So now we're ready to write my equation. My function will be x plus 2, but I need multiplicity 2, so I'm going to square that. Okay? Then I need x plus 1, multiplicity 1, and then I need x minus 1, multiplicity 3. So we're going to cube that one. Yeah? And it says write your equation expressed as the product of factors. So again, this is my equation in factored form. If they wanted it in standard form, you would have to multiply these all together. Okay? Oh, my leading coefficient. Both arrows are pointing up, which means that my leading coefficient, again, they want it to be either +1 or -1. Well, since both arrows are pointing up, I know that it needs to be +1, which you don't have to write, but you can. Okay, so there's my equation. Now it says use both the equation in part B and the graph to find the y-intercept. Well, I can see the y-intercept, but I can't count it very well. Now that we have an equation, I can find f of, if you're looking for a y-intercept, find f of 0, which is going to be See how I'm copying my function? I'm just leaving blanks where x's were. And I'm going to plug in zeros. So this would give me 2 squared. This would give me 1. That one's not squared, that's to the first. This would give me 1 to the first, and this would give me -1 cubed. So this is going to be 4 times 1 times -1, which is going to be -4. So I know that it crosses at -4, and it does. Now what I did is I went to my graphing calculator, and this is what I typed in for y equals, and notice that I got the exact same graph. I actually didn't cube this one in the beginning, and this was a lot smaller, and this hump was on the other side. And that's when I remembered, oh yeah, because that's flatter there, it's got to have a degree bigger than 1. Okay? Alright, so next they're going to ask you to do some interpreting. It says, experts fear that without conservation efforts, tigers could disappear from the wild by 2022. Just 100 years ago, there were at least 100,000 wild tigers. By 2010, the estimated world tiger population was 3,200. The bar graph shows the estimated world tiger population for selected years from 1970 through 2010. Also shown is a polynomial function with its graph that models the data. Use this information to solve exercises 73 to 74. Okay, what they did was they took this data and they called 1970 year 0, and they plotted the 37,500. 10 years later, it was 1980, and they plotted the point 28,000. 10 years later, which would be 20 years after the beginning, they plotted the 12,500. 10 years later, 30 years after the start, they were down to 6,300. And in 40 years later, 2010, it was down to 3,200. Okay? So, and that's how they graphed it. Alright? So this says, find and interpret f of 40. That means they're telling me to plug in 40 for x, which means I'm really using the year 2010. 40 years after 1970 is 2010. Alright? But to do the math, you can see up here I typed it in. Here's what I typed in on the calculator. You do 0.76 parentheses cubed minus 30 parentheses squared minus 882 parentheses plus 37,807. And inside those parentheses you plug 40 and you type it left to right with your parentheses, and you get f of 40 equals 3,167. Okay, so that's A. It says identify this information on the graph. That's this point right here. 40 years, we're right here at this dot. Okay, it says, does f of 40 overestimate or underestimate the actual data shown by the bar graph? By how much? According to the bar graph, the population in 2010 was 3,200. According to us, in 2010, it was 3,167. So if the real amount was 3,200 and I got 3,167, to figure out how close we are, we subtract. That's 3, that's 3, that's 0, that's 0. So we are off by 33. And my estimation is lower than theirs, so ours would be an underestimate by 33 tigers. Okay, it says use the leading coefficient test to determine the end behavior to the right for the graph of f. Okay, let's do that first before we continue reading. This is a third degree function. My degree is 3, which is odd, which means I'm going to have opposite tails. Okay, my leading coefficient is 0.76, which is positive, which means my second or my right tail has to point up. So according to my leading coefficient test, this thing has to come back up. Okay, so there's my end behavior. It says, will this function be useful in modeling the world tiger population if conservation efforts to save wild tigers fail? If we fail at our conservation efforts, this isn't going to keep going up. This is saying that the tiger population is on the mend and it's heading up, and it's going to continue heading up forever and ever and ever. Well, it's not going to head up if we fail. and we don't make the conservations. Alright, and then the last part of your homework, it's going to ask you to use a graphing utility with a viewing rectangle large enough to show end behavior to graph each polynomial function. Alright, let's see what I expect to see. First of all, my degree is 5, which is odd, so I'm expecting opposite tails. Second thing, my leading coefficient is -1. The negative means that I expect my right tail to go down. So whatever happens on this graph, my right tail has to go down, my left tail has to go up. And it could change, it could have 4 turning points. Okay, so that's what I'm expecting. I typed it in the graphing calculator, and I did a standard window, and that's all I can see. Well, that's not what I'm expecting to see. I'm expecting to see one tail up, one tail down, and some sort of wiggle in the middle. So my standard window obviously isn't going to work. And you guys just have to play until you get good at it. Okay? What I usually do is when standard window doesn't show me much, I go big. Okay? So I changed my window from my x's from -50 to 50 and counted by 5s. And again, I'm old. I've just learned that don't make your x's too terribly big. I go out by 50s when I'm trying to adjust a window to see what I want to see. I only change my x's by 20s, 30s, 50s in this case. All right. I've learned that y's usually have a bigger range. These functions have a bigger range. So if you see, I set my y min to -1000 and my max to 1000 and counted by hundreds. And this is the graph I got. And now I can see one tail up and one tail down. But I'm not seeing those 4 turning points. Okay, so I thought, well, maybe this is too big. So I played again, and I adjusted my window. And I went from -20 to 20, because clearly the graph is going to happen here, between here and here. Well, before I was counting by 5, so 5, 10, 50. So I went from -20 to 20, thinking that was, smaller. And then this was so squishy, I wanted to see more what was happening here, which means if you want to zoom in, you need to make the window smaller. So instead of going from -1000 to 1000, I went from -200 to 200 and counted by 20s. And now I'm not seeing it all, but I can get a pretty good, at least I can see kind of some turning points in there. And I could probably play some more and get an even better picture, but that's what they're going for. They just want you to be aware of what they call hidden behavior. And that's what's dangerous about using these graphing calculators. If you don't have the knowledge of what you expect to see beforehand, you're not going to know that this is a bad graph. Okay, that's why it's so important to have an understanding of what these functions are going to do before you even look at them. Okay, because when you use technology, you've got to be smarter than the technology. You've got to know ahead of time what did you expect to see, so that when your graph doesn't show that to you, you can make the adjustments so that you can. Alright, so we already answered those two. Apparently I was supposed to wait. Alright, and we are at homework, so we are done. Happy homeworking, and I will see you next time.